All right, let's dive deep into NumPy. We're going to go beyond just using it and really get to the bottom of what makes it the absolute cornerstone of scientific computing in Python. We're going to unpack the two big secrets behind its incredible speed and flexibility: vectorization and broadcasting.
So here's our game plan. We're going to build this up layer by layer. We'll start with the problem that NumPy was created to solve in the first place. Then we'll uncover the how behind its speed, explore the magic of broadcasting, see it in action with real code, and then we'll wrap it all up with some practical tips to make your own code fly.
Okay, so let's start with the why. Why was NumPy even necessary? It all comes down to a fundamental limit of standard Python, and that's the fact that its native loops are just, well, they're kind of slow when you're doing heavy-duty number crunching.
And look, the performance difference we're talking about here isn't just a little bit better, it's a completely different league. We're talking 10 to 100 times faster. To put that in perspective, that's the difference between grabbing a coffee while a calculation runs for minutes versus getting the result almost instantly. It is an absolute game changer, especially when you're dealing with the massive data sets you see in data science and machine learning. And you can really see the difference in philosophy right here. On the left, you've got your standard Python for loop. It makes sense. You read it, it goes one item at a time. But on the right, that's the NumPy way. A single, clean, elegant line that does the exact same thing, but with just incredible efficiency.
So, what's the secret sauce here? How can one line of code be so much faster than a loop that looks like it's doing the same work? Well, the answer is this really powerful concept at the heart of NumPy called vectorization. It all starts with NumPy's main building block, the ND array. And the best way to think about it is like a perfectly organized bookshelf, where every single book is the exact same size. See, unlike a regular Python list that can hold anything, an ND array demands that all its elements are the same data type. And this strictness, this uniformity, that's its superpower. It lets NumPy store everything in one big, continuous block of memory.
And that super efficient memory layout is what unlocks vectorization. It's basically the art of applying an operation to the whole array at once, instead of looping through it piece by piece. You remember that r times 2 from before? That's vectorization. You literally stop thinking about individual numbers and you start thinking in terms of entire arrays.
So here's the real trick. The loop doesn't actually go away. It just gets moved from the slow interpretive lane of Python into the high-speed express lane of optimized, pre-compiled C or Fortran code. NumPy is like this brilliant translator that takes your simple command and then runs it using these lightning-fast languages right under the hood.
And the benefits are just huge. Not only is your code way faster, but it's also cleaner. It's more intuitive. It often looks a lot like the actual math you'd write down on a whiteboard. And let's be honest, less code almost always means fewer bugs. But on an even deeper level, vectorization unleashes the full power of your CPU using things like SIMD, that's single instruction multiple data. It basically means your processor can do the same math on a bunch of different numbers all at the same time. It's a massive performance boost.
Okay, so let's take this one step further. Vectorization is amazing when all your arrays line up perfectly. But what happens when they don't? What happens when the shapes don't match? This is where one of NumPy's most powerful, and sometimes kind of confusing, features comes into play.
Right? Think about it. Maybe you have a matrix of student grades, and you want to add 5 bonus points to every single one. Or you have a column of house prices, and you want to compare each one to 3 different market benchmarks in a row. Do you have to just give up on vectorization and go back to writing those slow, clunky for loops?
Thankfully, the answer is absolutely not. NumPy has this incredibly elegant solution called broadcasting. It's really just a simple set of rules that makes vectorization way more flexible, letting you perform operations on arrays that have different but compatible shapes. The best way to think about broadcasting is that it's like creating a phantom array. NumPy conceptually stretches the smaller array to match the bigger one. But, and this is the magic part, it never actually uses the memory to create that bigger array. It's like having a ghost that does all the work without taking up any space. That's why it's so fast and so memory efficient.
And you know what's wild? The rules behind all this power are actually super simple. To figure out if 2 arrays can be broadcast, NumPy just compares their shapes, dimension by dimension, starting from the right. A pair of dimensions works if they're equal, or if one of them is a 1. If that's true all the way down the line, you're good to go. It really is that simple.
Okay, so let's look at the most basic example you can imagine. We're adding the number 1 to an array. NumPy looks at this and just goes, yep, no problem. I'll just stretch this one number to match the whole array shape and add it to every single element. This is broadcasting in its simplest form.
And this is where it gets even cooler. Here we have a 2x3 matrix and a vector of length 3. So NumPy compares their shapes, 2, 3, and 3. Starting from the right, the dimensions match. They're both 3, so they're compatible. Then NumPy just conceptually duplicates that vector for each row of the matrix and does the addition. It's so clever.
Okay, we've got the theory down. Now let's see how this actually plays out in code. Let's look at some examples to see where broadcasting really shines, and, maybe just as important, where it doesn't work.
So in this first one, we're adding a vector with a shape of 3, to a matrix that has a shape of 4, 3. Because they're trailing dimensions, the ones on the right, both equal 3, the rule is satisfied. And boom, NumPy broadcasts the vector across all 4 rows of the matrix, and the addition just works perfectly.
But what happens when we break the rules? Well, check this out. Here, the matrix shape is 4, 3, and the vector is 4. When you compare their trailing dimensions, you get a 3 and a 4. They're not equal, and neither of them is 1. The broadcast fails. But here's the great part. NumPy doesn't just crash. It gives you this super helpful value error that tells you exactly which shapes couldn't work together. And that is a lifesaver when you're debugging.
So, if you're trying to wrap your head around the difference, think of it this way. Vectorization is the car, and broadcasting is the GPS. Vectorization is the powerful engine that gets you where you're going fast. Broadcasting is the smart navigation system that helps you handle all the tricky intersections when your arrays don't have the same shape. Broadcasting exists to make vectorization even more powerful.
Okay, so now that we've pulled back the curtain on the why and how of NumPy's crazy performance, let's get practical. How can you take all this knowledge and use it to make your own code faster and more efficient?
Here are your golden rules. First, and this is the big one, always vectorize. Ditch those Python for loops. Second, pick the smallest data type that works for your numbers, like an int 32 instead of the default int 64. It can cut your memory usage in half. Third, if you know the final size of your array, pre-allocate it. Appending is slow. Fourth, use in-place operators like plus equals to modify data directly so you're not creating temporary copies. And finally, understand that slicing an array creates a view, not a copy. It's super fast, but just remember, if you change the view, you change the original data too.
So, when it all comes down to it, really mastering NumPy is about more than just learning a library. It's about changing the way you think about a problem. It's learning to see the whole array, the whole data set, instead of just focusing on one element at a time. And once you make that mental shift, from thinking in loops to thinking in arrays, you unlock a whole new level of power and efficiency in your code. The real question is, are you ready to make that shift?